A very good day. My name is Kame, matrix ID AE210056. My supervisor is Dr. Nabiha. So I would like to start my presentation with my project titles, which is called Low Power AES using ASIC implementation for IoT applications. So with the advancements of IoT applications, such as the smart city, smart home, wearable device, and also the connected car, so the security issues become crucial in order to avoid the data to be attacked by the intruders. So one of the ways to protect our data from intruders is using cryptography. So it has two essential procedures, which is called encryption and decryption. The cryptography can also be divided into three, which is called symmetric, asymmetric, and hash function. So for the symmetric encryption, we have AES, DES, and 3DES. For asymmetric, we have ECC, DSA, and PGP. And for last, the hash function, we have SHA-1, SHA-2, and SHA-3. Okay, so the cryptographic algorithm that I choose is AES, which is called Advanced Encryption Standard. So it is a symmetrical key algorithm and it can be implemented on both software and hardware. So the AES will have three different key lengths. For different key lengths, it will have different round of transformation. So for my case, I use the 128-bit of key length. So it will have 10 round of transformation. So as you can see here, the plain text will first go to the first round of transformation, which is add round key with the round key here. Then it will go to the repeated round, which has 4 transformation operations, which is called sub-bytes, shift rows, mix column, and add round key. So for the last round here, they will have a slightly different. There is no mix column as the repeated round, but after the last round of transformation, the system will generate the output, which is called ciphertext. The problem statement for my project is the side channel attack. It can be carried out by monitoring the physical output of the devices, such as the power, heat, time, and also the sound. So the power is the most significant because it can generate predictable power patterns that can be monitored by the hackers, so they can get our data easily. So as in conclusions, the higher the power consumption leakage, the risk to be attacked by the intruders will be higher. So it's clear that the general AES is not strong enough to protect our data. So the low power AES using ASIC implementation is being designed with the purpose to optimize the power consumptions. For methodology, so here is my design project flow. So my project will be started with the research on the AES algorithm. Then I do define the suitable AES specification for the IoT applications. Then I write the Verilog-based AES architecture design. And next, I simulate the design by using the Synopsys VCS to observe the functionality. So if I didn't get the ideal result, then I will go back to here, which means I need to debug and also rewrite the Verilog code. If I get the ideal result after simulations, then I will go to the design synthesis by using the Synopsys design compiler. So in here, I will do the PC setup, design compiler setup, and also define the certain design constraint for my design. So next, I will check whether my design can pass the synthesis and also the optimization, which is using the clock gating method. So if no, then I will go back and debug my RTL code. Then if yes, I will proceed to the physical implementation and also the verification. So this step will be proceed inside the Synopsys IC compiler. So I will get the layout design and I will proceed with the design verification to check if my project can meet the DRC and also the LVS check. So if no, then I will doing the layout design again. And if yes, then end of my project. Here is the block diagram of my design. So you can see from this side, here is the part for key expansion operations. So you can see the key in, key input, and it will go to the key expansion box, and it uses the round constant to expand the cipher key, and then go for further transformation, which is the add round key here. So for here, which is the input data, and here we will have the input register. So the input register will then pass the data to this multiplexer. This multiplexer is actually used to determine if this is the first round of our transformation. If yes, then it will choose here as the input. If no, then it will choose here as the input. So the output of the multiplexer will then connected to the add round key here, and it will pass to the round register here. And you can see here, there is a box for the transformation operations, which include the sub-bytes, shift rows and also the mixed column. So this multiplexer is used to determine if this is the last round of operations of the transformations. If yes, then it will choose the output from the shift rows box then as the input. If no, then it will choose the output from the mixed column as the input. So the output of this multiplexer will then connected to this multiplexer, and it will pass to here. So for examples, if this is the last round, then it will choose the output from the mixed column and then bring to these multiplexers and go through to the add round key transformation and then generate the data out, which is the output data. For the result part, I performed the functionality verification through the simulation in Synopsys VCS. So for the simulations, I have used 3 sets of test vectors that published by the NIST. So as you can see here, they share the same cipher key, which is 2B7E something, and then with the different plain text. So they will have different ciphertext, which is the output. So as you can see here, there is the screenshot for the simulations from set A to set C. And besides that, I also use the latency, which is the time taken to complete the encryption operations to calculate the throughput for my design. So, and the output will be 0.032 gigabytes per second. So next will be the design synthesis by using the Synopsys design compiler. So let's go to the design compiler GUI view.
To say when everything gets in the way, seems you cannot be replaced, and I'm the one who will stay. Oh, in this world, it's just us. You know it's not the same as it was. In this world, it's just us. You know it's not the same as it was. As it was. As it was. You know it's not the same. Answer the phone. Harry, you're no good alone. Why are you sitting at home on the floor? What kind of pills are you on? Ringing the bell and nobody's coming to help. Your daddy lives by himself. He just wants to know that you're well. In this world, it's just us. You know it's not the same as it was. 'Cause in this world, it's just us. You know it's not the same as it was. It's not the same as it was.
Okay, so here is the summary for the report from the synthesized design. So there is the 28% of improvement for the aspect of total power consumption for my design, which is from 0.87 milliwatt and then it decreased to 0.62 milliwatt. And for the timing performance, so we need to look at the timing slack. So it is in positive value, which means it is operate as normal. And here is the slightly improvement from the aspect of total synthesized area, which is from 0.037 millimeter square to 0.035 millimeter square. So after the design synthesis, maybe the physical implementations and also the physical verifications by using the Synopsys IC compiler. So for the physical implementations, I have performed it by using the operation which is called place and route onto the netlist that export from the design compiler. And for the physical verifications, we will conduct by using the design rule check, which is called DRC, and layout versus schematic, which is called LVS. So you can see from the picture here, here is the layout window after I do the setup inside the Synopsys IC compiler. So what I do is export the DDC file from the gate level netlist inside the design compiler, and then I modify and also verify the DC setup files with the correct path and also the libraries. So I also do conduct the floor planning for my design. So the 0.7 here stands for 70% of core area will be used for placing standard cells. And the aspect ratios for 1.0, which means the design will be in square core. And then the 20 microns for foresight, which means the space between the core boundary and pass will be the same, which is 20 microns. So you can see here is what happens after doing the floor planning. Here's the cell placement area, and the light blue color is for input I/O pins. Then here is the region for the cell to be placed within the die. So I also doing the power planning, which is set up the core rings and also the horizontal power strap. So I set the offsets for 0.5 units and also the ring width for 5 units. So as you can see here, the horizontal power strap will have the same metal layers with the left and right side of the power rings. This is because if you use the different metal layers for these two things, then it will occur errors, which is called openness later. So next will be the view for the power planning stage of my design. So as you can see, here's the core rings, and for left and right sides will have the same metal layers as the power strap. So after this will be the placement of logic cells. So what I do is just insert the command, which is called place optimizations. So it will conduct the placement of logic cells by legalized placement, which can ensure there's no any overlapping cells. So next I also conduct the clock-free synthesis. So since I haven't mentioned any parameter like the latency, routing metal, and so on, so the system will use the default settings for the clock-free synthesis operations. So what happens is the clock signals will be distributed to every region through the clock-free. So it constructed for 6 levels, which is from level 0 to level 5. So it also balances the clock load minimal levels that display considerable fan out, such as this 402 endpoints for level 3. It also enables the reduction of skews and also preserve the timing integrity over the design, so it can comply the intended clocking structures. The next will be the routing. So for routing, we have 3 stages. The first one will be the global routing. So in here, the networks will loosely distributed and according to the congestion. And next, the track assignment and details routing. So in here, the horizontal and vertical tracks will be allocated. And for the last stage, which is called search and repair, in here, the DRC will be eliminated during the details routing, search and repair. So after routing, my supervisor got asked me to measure the area for the design by using the internal ruler from the Synopsys tools. So the total area will be 0.047, which is slightly bigger than the synthesized design. So this is because the layout has including the power rings and the strap areas. It also includes the core margins and also the clock-free synthesis insertions. So next will be the physical verification part. So the first check will be the design rule check, which we usually call DRC. So what it do is to verify if our design has meet the physical constraint that is associated with the fabrications. So by observing the report here, so it's clear that there's no any violations since it shows 0 here. And then the place and route also has been completed throughout from layer 1 to layer 9. So this indicates that the signals and the power distribution networks has been properly implemented. And for the last will be the connections has been correctly routed because there is no any open and short nets inside the design. Next will be the layout versus schematic inspection, which we usually call LVS check. So it used to compare the original schematic, let us to verify if this match with the post layout netlist after routing process. So here is the summary for the report. So there's no any floatingness, shortness, openness, electrical equivalent error, the mask joint error. So as a conclusion, all the circuit elements and connection has been perfectly matched. So as an conclusions, all of the objective for my project has been achieved. For the first one, the AES 128 encryption architecture has been developed by using the Verilog code and has been applied onto the 32nm CMOS technology node. The functionality of my design has been validated by using 3 sets of test vectors that published by the NIST inside the Synopsys VCS. So the output indicates a successful encryption functionality for my design. And next will be the clock gating method that has been applied to my design with the purpose to optimize the power consumptions. So as a result, you can see there is a very significant optimizations for dynamic power, which is around 42%, and also the total power consumption about 28%, which is from 0.87 milliwatt to 0.62 milliwatt. So this reduction has been performed without sacrificing any timing closures and also the performance of the design. And last will be the physical implementations, and the verification has been completed by using the Synopsys IC compiler. And a small design area has been measured, which is 0.047 millimeter square. So last, the proposed design is defined as physically feasible for ASIC implementation because it has meet both the minimum performance and also the power requirements. Thank you.